Welcome back, grade 12 learners, teachers alike. We are continuing with the electric circuits. We dealt with Ohm's law, especially in terms of definitions, definition of Ohm's law, equation, graphs, which are two, and then the ohmic and non-ohmic conductors. Please always take notes of such comments because they are very vital when coming to the answering of questions in the examination. Now let's move on to power and energy dissipation. We'll start with energy. Energy dissipation, we're coming from grade 10. And in grade 10 we learned about that the voltage is the amount of work done or amount of energy required to move a 1 coulomb charge in this case, or per coulomb charge. Now coming from this formula, then where W represent the energy or the work done, then we'll have W equals to VQ. But we know from grade 10 as well that the current is defined as the rate of flow of charge. Current is defined as the rate of flow of charge. Yes, from this formula we'll find that therefore the charge will be the same as current multiplied by delta T. Then if we represent it here, therefore we'll have the formula of energy will be VI delta T. So if you've got the potential difference in the current and how long the current is flowing in the circuit or across a component, you can always calculate the energy dissipated in that component. Now if we introduce Ohm's law in this one to say, we know that R equals to V over I, that is Ohm's law. Therefore we can now come up with the formula. If we make V in terms of I and R, therefore it will be IR, then which will give us the formula of I squared R delta T, whereby resistance is known and the current flow in that the resistor is known. Then we can calculate the energy dissipation using this formula. Again, then we can also move where now we change I in terms of V and R. Therefore I will be the same as V over R, then V multiplied by V will be V squared over R multiplied by delta T. So these are the formulas that we can use for energy dissipation in a component in the circuit, including the battery. Now in terms of power dissipation, we know from power to say power is the rate at which work is done. I think that one should be known. From the definition, power is the rate at which work is done. Therefore, if we use this one, energy as VIT, therefore we'll end up with the first formula for power as VI. Because delta T will cancel delta T, then this is the first formula. Then from here, it shows that with power, we just remove the delta T. Therefore, then the second formula for power, it will be now power. If you make V in terms of IR, it will be I squared R. If I know the current flow in the component and the resistor, then I can always calculate the power dissipation there in that component. The last one will be now power will be V squared over R. If I know the voltage and resistor, then I can always calculate the power dissipation in that component. Very important in this case. But now the brightness part, the brightness of the bulb, there's the issue about the brightness of the bulb, then you need to know that one. Okay, let's make it a few points about the brightness, because they might ask you about that brightness of the bulb in a circuit. Brightness of the bulb, then we'll only consider two things in this case. That is a series and parallel connections here. What will be the brightness of the bulb when the cells are connected in series? Now in this case, for series circuit, in this one, bulbs in series. But let's just make a note here to say, remember, as the power increases, as the power, if you calculate and find that the power increases, it means that now the brightness also increases. Brightness increases. Simple example can be a bulb of 60 watts is dimmer compared to the bulb of 100 watts. So as the power increases, then the brightness also increases. The 100-watt bulb will be brighter than the 60 watts. So that's what you should know. Thank you. Therefore, for bulbs in series, when bulbs are in series, then what you should know is that very important that power will be directly proportional to the resistance. What does it mean? In this case, in words, we can just write it to say power is directly proportional to the resistance. So resistance there. So meaning that now in that combination, as the resistance increases, this is the conclusion now, meaning that if the resistance increases, then the power also increases. So that is the case here. Fine. And once the power increases, so it means that also the brightness will increase. Brightness increases. That is when you are connecting resistors in series. Then now bulbs in parallel. What can we note out of this one is that the first point will be now the power is inversely proportional to the resistance. Power is inversely proportional to the resistance. Very important. Please note that I want to say if we are connecting resistors in series, therefore what does this mean? It means that now if the resistance increases, increases, the power decreases. And that if you want to, the fewer resistors are connected in series, in parallel, then the brightness of those bulbs. So the more you connect bulbs in series, in parallel, then it means that the brighter they become. So that's what you should know. Therefore, means that the brightness also decreases. Brightness decreases because we say brightness and power are directly proportional. Once the power decreases, then the brightness will decrease as well. If you want to increase the brightness, you have to connect now, you have to decrease the resistance now. I mean that you connect now more bulbs in parallel. So as we know that if the more bulbs are in parallel, the total resistance decreases and the current will be increasing. Hence now the power according to I squared R, then it will increase as well. So okay, fine. That is about the power dissipation and the energy dissipation in the circuit. Now let's go to this one of EMF and the internal resistance. Internal resistance. This is the resistance inside the battery, but by definition is the way it happens. To say this will be now the resistance you can say inside the battery or within the battery, inside a battery or within the battery. That drops the potential difference of the battery. Potential difference of the battery when there is a current. When there is a current in the circuit. When the current flows in the circuit, then the potential of the battery drops. For example, you'll find that now if I've got a battery and then with internal resistance, and then there is a main switch, and then maybe just a resistor, and the current here, the ammeter reading. Now this is switch S. When S is open, you'll find that now, let's say for example each cell has got 3 volts, so the EMF will be 6 volts. If you connect the voltmeter across the terminals of the battery in this case, then you will find that now the reading on the voltmeter will be 6 volts. So EMF is 6 volts and the V will also read 6 volts. But when the S is closed, and that now there is current flowing now in the circuit, what's going to happen is that now V now will be less than 6 volts. Argument's sake, hypothetically, it can be 5.6 volts. I mean that now there's a lost volts when the current is flowing through here due to what? The internal resistance. That's why we say this is the resistance at the battery that it drops the potential difference. The potential difference drops from 6 to 5.6, drops the potential difference now of the battery when there is a current flowing in the circuit. That's about the EMF. This one, the internal resistance. So which means that now if the total voltage is 6, the total voltage is 6 volts, but when there's no current flow in the circuit, then now the voltmeter will reach 6 volts, then plus 0. When S is open S, closed S, you will find that now we still have got 6 volts of the battery, but now this is 5.6 volts plus 0.4 volts. So therefore, if this is the EMF, this will be the external voltage, and then supplying the external circuit, and this will be the internal voltage. That's brought us to one most important expression in this circuit about the EMF. That's why when we talk about the EMF, which literally means electromotive force. Now, but by definition, the EMF will be maximum energy supplied by the battery per Coulomb charge or per unit charge. Now that is the EMF, maximum energy supplied by the battery or maximum work done by the battery. Maximum energy supplied or maximum work done by the battery. So we are guided by this formula, V equals to W over Q. That's where we get the definition from. So the maximum energy or the maximum work done by the battery per Coulomb charge, that is the EMF Hopefully we know the definition of EMF by now, and then we'll talk more about the internal resistance and the EMF in the next session, involving calculations when the internal resistance is ignored or when the internal resistance is considered. Remember, in grade 11 we're saying it's very small, it is negligible, but in grade 12 now we consider both. It can be ignored or it can be not be ignored. Majority of the question, the internal resistance will not be ignored, so you must know that. For now, let's just pause and then we'll continue with this session. Thank you.